All right. Now that we're done with the section questions, now let's just practice everything else. Our first question in these extras are: suppose you take a plastic ring of radius A and glue a charge on it so that the line charge density is lambda naught magnitude sine theta over 2. And then you spin the loop about its axis at an angular velocity omega. Find the exact scalar and vector potentials at the center of the ring. Okay, let's draw it out, shall we? All right, so we have the xy plane. Omega t is the angle. Then we have theta and phi, of course, sweeping through everything with some radius a. So here, the charge distribution lambda of phi and t is equal to lambda naught absolute value sine theta over 2. And here, from the diagram, they tell us that theta is equal to phi minus omega naught, or not omega naught, omega t. Okay, so the retarded scalar potential at the center is given by TR is equal to T minus script R over C, which is equal to T minus A over C, which is a constant. Cool, we like that. So then the scalar potential with this form, we just plug in the lambda for the rho. And now we just need to be careful with how to calculate everything. Again, for a circle, we go through 0 to 2 pi. Pretty easy to deal with there. That script R is A, so we just plug in A. And then our DL is A d phi. So cancel. The A's, nice and easy. That lambda naught comes out. And we're just left with this gross integral of what is sine of theta over 2 d theta once we do a substitution on it. Easy enough. And then we just get the cosine and all that other fancy jazz. We see that the negative 1 minus 1 gives us the negative that we need to cancel. And we're left with V R of t is equal to lambda naught over pi epsilon naught. A quick note on this that we need to be careful of is that at any fixed retarded time, d phi is equal to d theta. Okay, so the switch is pretty easy to deal with, and it goes through one full cycle of phi or theta, so it doesn't really matter. We just have to be careful of what it means to be with the retarded time, which in this case is going to be constant since it's always on the circle generating and the charge is distributed as such. Okay, so moving forward then, what we see is for I phi of t, that's just equal to lambda times v. But again, that's linear velocity. We need angular velocity, hence a omega. Okay, so with that, we have phi, or not phi, but lambda naught, absolute value sine theta over 2, a omega in the phi hat direction. Okay, that is the rate at which it's rotating. So with that, or the direction, not rate. So with that, the vector potential, we just have to plug in the I for the current density J. And again, we see that the script R is A, and we see that our DL prime is A d phi. So we have a lot of constants to push out the way, namely lambda naught, omega A, and now we're left with this gross absolute value of sine phi minus omega TR over 2, phi hat d phi integral. Here, TR is equal to T minus A over C, again, constant. So for the phi integration, we have mu naught, lambda naught, omega A over 4 pi, 0 to 2 pi for phi. And now we have to put in the phi hat coordinates, the unit vectors, from, again, the things we found in Chapter 1. Nothing too crazy here. We just have an extra sine and cosine phi to deal with as a result. Again, if we switch variables so that theta is equal to phi minus omega tr, the integrate from 0 to 2 pi. So we don't have to worry about the absolute value. We see we're positive there. Easy enough to deal with because the reason why we drop the absolute value is theta over 2 pi over 2 gives us pi, so we're still in the top hemisphere as far as theta is concerned, so we're all positive for sine. Easy enough. But that being said, now we have to substitute in for phi in the from the phi hat, for the sine and cosines there, and we can split them up into two different integrals by distributing them, and so hence the blue and purple. And then so we see that we have a product of sines with different angle measures. So solve these integrals separately and sub back in. So that's what we do. We use the sum and difference identity on, or the product rules with them. And then, all the trig identities that we forgot about. And simplify down as best we can because it's always a mess. Simplify, simplify, simplify. Similarly, do the same for purple. Again, with the products, split up that integral, evaluate down. And as you see, we get, for the blue integral, we get -4/3 sine omega tr. Not really that unsurprising, consider how we had so many 4/3 from sine cubes before. But also what we see for the purple is that we get -4/3 cosine omega tr. Okay, so maybe we aren't too far out of bounds for this anyways. So we factor out after we cancel the negative and the 4s, and we see that we get a mu naught lambda naught omega a over 3 pi sine omega tr x hat minus cosine omega tr y hat. And then we just plug in the definition for TR and we get the vector potential, that is the exact, and we are good to go.